Hi everyone, we're going to continue on with chapter 9. So we're moving on in terms of theory from talking about gases and then mixtures of gases. That's how we ended on chapter 8, talking about Dalton's law of partial pressure. We're now moving in terms of complexity into what happens when we're dealing with solutions. So it's going to be a mixture of particles. So how does the mixture behave compared to when they were separate components? So for this particular video, we're going to go through sections 9.1, 9.2, and 9.3. So we're going to first start by defining what a solution is. So we need to remember, going back to chapter 2, I believe, is what is a homogeneous mixture. So homogeneous mixture is any mixture in which I could take something, say, from the top of a solution and from the bottom of a solution, and once things were mixed, they'd be identical. It doesn't matter where I choose from the solution, they would all be identical. In the picture currently shown, you're in the process of mixing, they would be heterogeneous, so not the same, but once the solution has been mixed thoroughly, the solution would be homogeneous. And if we break that down, it's a weird mixture of Greek and Latin, but it's homogeneous, so it is the same mixture, so the same type of things mixed together. So for us, we won't go beyond two components. A two-component mixture is called a binary mixture, binary meaning two. So you're going to have two components. One is going to be the solvent, and that's going to be whatever component is the larger amount. Then you're going to have the solute. The solute is going to be whatever is in the smaller amount. The way that I remember this is that solute is going to be the minute, so minute component. So it looks like the word minute. That's because it's spelled exactly the same as the word minute, but it comes from the same etymology, being a smaller component. So a minute is a small component of an hour. A minute component, or solute, is a small component of the solution. And so that's how we want to think about those two words, because it confuses a lot of students because the first three letters are exactly the same. So that might be a challenge. So what are solutes? So we have a solvent. A solvent is going to be the compound that things just dissolve into or solubilized into. So we need to expand probably what most people's first inclinations are towards what a solute is. When we think of solutions, we typically think of liquids. But a solute is also, and solutions are also can be described as either liquids, gases, or solids. So they can be made out of different phases. When they mix, by definition, to be a solution, they need to be spread evenly. That is homogeneous. Heterogeneous would be if they were not mixed evenly. Heterogeneous solution would be like if you pulled out salad oil, right? You can see the separation between vinegar and oil. There's a demarcation. You can see they're completely separate. But if you have a saltwater solution, like if you went down to the harbor and pulled out water, well, the water and the liquid, the water and the salt, right, they're behaving as one. So that'd be a homogeneous mixture. However, even though in our first bullet point, we said the solids can be liquids, gases, or solids. Once the solution is made, solute and solvent will have the same physical state. What do I mean by that? Well, if I took sodium chloride, which is table salt, I mean, it literally looks like a shaker of salt, and I dissolve that in water, H2O, right? It will dissolve and actually become the same state as the water. It will now be an aquated solution. So it is no longer behaving as solid, it behaves in aqueous solution. The water used to be a pure liquid, but now it becomes a solution. these two, the sodium chloride, once it's been aquated, and this H2O will behave as one unit. That's what makes a solution different than just a random mixture. They behave as one. And another thing too, and I think most people are familiar with this, is that solutions are not visible, right, but can give a color to the solution. Typically, when you solubilize something, it is clear, but that is not always the case, right? So it can be clear. An example of that would be, say, a salt solution. But an example of a colored solution might be copper sulfate. Copper sulfate, when it's dissolved in water, will be blue. Not that the water is blue, but the copper itself actually is interacting with light differently, and then you perceive that as blue. Another aspect of a solution is that it cannot be separated by filtration. So if you had a water and sand mixture, so water and sand, right, if I passed that through a filter, I'd pull out the sand. The water would go through. Imagine passing it through a coffee filter. However, if I had a salt solution again, and you can prove this to yourself too with a coffee cup, a coffee filter, put a saltwater solution in there, I guarantee you the salt will go through, because the salt and the water have made a solution and behave as one. So that is the key difference between a homogeneous solution and a heterogeneous solution. I am still trying to move between slides. I'm working out, oh, here we go, almost. Still working out the kinks of moving between slides. I'm using 3 different programs at the same time. So far it seems to be working. It's just going to take a little bit until I get comfortable switching between them. So, how does this look, right? So, I have put up an image on the screen where we see we have a starting state. Here is a solution on the very bottom. Down here is copper sulfate. Copper sulfate, so CuSO4. There's our polyatomic ion sulfate and our metal copper. The way it's shown down here is that the blue balls down here are going to be copper, and then the gray ones are going to be sulfate. They started as some sort of solid. That's going to be here. So when we add this solid, copper sulfate, to a cylinder full of water, eventually, you didn't say how fast it's going to happen, it'll take a while, but eventually water is going to pull the copper sulfate into solution. What it's going to do is now it's going to be a pretty even mixture of sulfate and copper. In this case, well, copper will be an ion, sulfate will be a polyatomic ion. We can actually see the distinct change. Here, in the first scenario, we have water. You can actually even start to see that it's dissociating in because it's a slight blue color. But there's a distinct barrier between the copper sulfate and the water. In this second figure, or second part of the figure, we can see that the copper sulfate has now been aquated. How can I tell? Well, the entire thing is now evenly bluish in color because the copper is interacting with light. The copper is the same at the top as it is in the bottom. In this case, it's going to be in the form of copper 2+ ion coupled with a sulfate anion. So types of solutions, right? I mentioned they can be a mix, no, not necessarily a mixture of different states. When they mix together, they'll behave as one state. So, types of gas solutions. Well, we have gas. The most common one example of a mixture that we're familiar with as a gas is going to be air. The solvent is going to be nitrogen because air is 80% nitrogen. And the solute is going to be oxygen gas because it's a little bit less than 20% because the rest make up that small little fraction between the two. So we can easily see nitrogen, major component, oxygen, minor component. We also have liquid solutions. So we can have a gas in a liquid. In this case, think about soda or even household ammonia. Right? So now we're talking about disinfecting things. A lot of people are probably using ammonia to disinfect. So in both cases, our solvent or the compound that's in greater excess will be water, but we'll have different solutes. If we're just talking about soda water or anything like soda, we know it's carbonated because the word carbonated is because of carbon dioxide being dissolved in the water. Ammonia gas is actually dissolved to make household ammonia. We can also have a liquid-liquid mixture. So vinegar would be an example of a liquid-liquid mixture. Again, the primary solvent is going to be water because the major component is water, but acetic acid is going to be the minor component, and that's what gives that little kick to vinegar because you're actually drinking acid. But a very, very small concentration. So it gives it that pleasant, vinegar flavor. Solids can also be dissolved in a liquid. So think of seawater. If you went down to Boston Harbor, again, water is going to be our solvent. The ocean is primarily water. There is a small amount of sodium chloride dissolved. In seawater, there's more than just sodium chloride. There's magnesium chloride, vanadiate. There's a bunch of other stuff, but predominantly sodium chloride. And then what we'll introduce, and this is probably a new one, is solid solutions, right? So a solid solution is actually called an alloy. And you might have heard that phrase before, so maybe brass or steel. Brass and steel are metals, but they're not considered elemental. Why? Because brass is actually copper dissolved, is used to dissolve a small amount of zinc. Steel is primarily iron, dissolved a small amount of carbon. And so, since they are not pure metals, they're actually a mixture, it will be technically a solution of metals, despite being solid. So what we noticed in that last slide is that water was a solvent in a majority of those examples. There's a reason for that. Well, we evolved on Earth. Earth is mostly covered in water. When we get into biological processes, when we get to the part of biochemistry later in April, we'll find out why water is so important to biology. But we're on Earth. There's a lot of water. Water is a primary solvent for a lot of the chemistry that we investigate as a chemist. So it is one of the most important solvents in nature, period. It is very important. You are, I believe, 60% water, right? Almost all living things, or all living things as far as we know, require water. Why is this important? Well, water is a polar molecule. It has these OH bonds. So what we're seeing here, there's an O. Oops, it gave me a lasso tool. I wanted to highlight things. There's an O, and it's forming a hydrogen bond with an H from a neighboring water molecule. And the same thing here. There's an O forming a hydrogen bond with another neighboring water molecule. Because water is polar, that means it's going to dissolve polar solutes. So water dissolves polar molecules. I can't spell. Hold on 1 second. I'll spell that right. P-O-L-A-R-M-O-L-C, molecules. And like I said, when we get to it, we'll talk about why this hydrogen bonding is very important in biological compounds, mainly because it's involved in keeping DNA strands anti-parallel. So we'll have one DNA strand going up, the other one going down, and it's not necessarily held together by hydrogen bonds, but it helps keep the code consistent. And then we'll also talk about why enzymes and proteins rely on hydrogen bonding to partially keep their shape, but mostly for their chemistry that they do in your body. But we'll get to that when the time gets there. So, can we predict if something will form a solution? And yes, we can. So we talked about previously that to determine if a molecule is polar or nonpolar, because we talked about electronegativity. Electronegativity. Right? We would say something like hydrogen fluoride is going to be polar, because if we're looking at what molecule is more electronegative, well, fluorine is more electronegative than hydrogen. How do I remember that? Because of the periodic table. I remember electronegativity follows a trend like I've drawn at the top of the screen. So, if something is polar, the solute, it's going to dissolve in a polar solvent. If something is nonpolar, it will dissolve in a nonpolar solute. If we have conflicts, like a polar and a nonpolar, they will not mix. An example, well, actually, when we do it on the example on the second one, a nonpolar solute might be oil. A polar solute definitely is water. That's why your salad dressing separates. They will not form a solution because oil is nonpolar and water is polar. When you have something like salt water, NaCl is polar, water is polar. That's why they dissolve. So that brings us into solutions with ionic solutes, right? So you do not need to be an ion to dissolve in water, though they do typically readily dissolve in water. So when we look here, it says sodium chloride crystals undergo hydration as water molecules surround each ion and pull it into solution. So what we see is here is a crystal of sodium chloride. Water will come and approach, and you can see that the partially negatively charged oxygen is starting to pull on that positively charged sodium. The same thing's happening over here, where the partially positively charged hydrogen is starting to pull on that negatively charged chlorine, and the same thing with that one. What ends up happening is ultimately the water will orient itself with the partial negative ends of the oxygens pointed towards the sodium plus, and what we see here is those partial positives on those hydrogens are pointing towards the negatively charged chlorine. This is what leads to that homogeneous solution, that we're forming these solubilization complexes. We start as a solid, dissolves in water, they separate into ions. This is called dissociation. So what happens if we mix two liquids together? So the last example was mixing a solid sodium chloride with a liquid water. So what we have here is a polar molecule such as methanol, and that's what we can see here, methanol. CH3OH is soluble in water because methanol has a polar bond, an OH group. We know it has a hydrogen bond donor and a hydrogen bond acceptor, so we're in good shape. And it can hydrogen bond with water. So we look at them as separate compounds. So there's, imagine having pure methanol and then pure water. And now let's take a look what happens when we mix them together. So here we can see, well, there's a molecule of water, there's a molecule of methanol, and what do we see between them? Well, they're forming a hydrogen bond. And so what you've done, yes, you've disrupted the network between all of the water molecules, which are much more tightly compacted, and you also have a more compact matrix between all of the methanol molecules. So we've made this solution now because we have a polar solute, the polar solvent, it forms a solution. So now we're on to 9.2, so electrolytes and non-electrolytes. All we're really going to do is define what each are. So strong electrolytes. Strong electrolytes, oh, my bad, it went back. So strong electrolytes dissociate 100% in water. The way we insinuate that something has been 100% dissociated is to use a unidirectional arrow, so in one direction, by writing what the solvent is above the line. That means it is going to be a strong electrolyte. It's going to be able to conduct an electrical current. So if you have a solution of sodium chloride, and then you actually attach a power source with a light bulb to it, it will light up. That is a strong electrolyte. 100% dissociated. It means all of this NaCl is gone, in the sense that it's gone and is a solid compound. It only exists as aquated anions and cations. For weak electrolytes, they only slightly dissociate in water. And the way we represent that is by this bidirectional arrow. So we see one is going forward, one is going in reverse, and they're dissolving into water. What that means is only a less than 100% dissociated. That means a sizable amount of the reactant actually remains. So there's some percentage of the hydrogen fluoride, while a smaller component forms H plus and F minus. So unlike our last slide when it went completely to products and completely dissociated, it is only partially dissociated. But what we see, if we actually could do this in class, which was my plan, is we can set up a battery, dissolve something that is a weak electrolyte, and what you will actually see is the light will turn on, but if you use an incandescent bulb, it will be only slightly turned on. Compare that to in the last slide, what was very bright. Now we have a more dim light, and that's exactly what you would see if we did this in real life, and I was going to show that to you in lecture. Not going to be the case. The last bit we're going to talk about in here is going to be non-electrolytes, and it's exactly what the word sounds like. It's not an electrolyte. If it's dissolved in water, it does not produce ions, and it does not produce current. So the sucrose might actually dissolve in water, but sucrose didn't form any anion or cation. To be conductive, you must form anions. If you put glucose into water, or sucrose in this case, and put it into and give it some sort of power supply, it does not light up the battery because electricity cannot flow through the solution if there's not a negative and positive cation and anion. Right? We see here, we have our positive, what we see here, positive cation, negative anion. We go even further back. Again, we double check. Positive, negative. We go forward. We don't have any charge here. Not an electrolyte. Will not conduct electricity. So there's our summary. Strong, weak, and non-electrolyte. So this will be the last thing we'll cover in this particular video lecture series. It's going to be on 9.3 in solubility. Why do things dissolve in each other? And how do we express that? So, solubility. It's going to be the maximum amount of solute that is dissolved in a specific amount of solvent. We'll talk about this in a future slide, but temperature will affect how solutes dissolve in water. It will also depend if they're going to be solids or gases. And what we usually express concentration as is an amount of solute per an amount of water. So I'll specifically say an amount and an amount. That seems pretty obvious, but what we're going to find out is that the units, even though right here is representative of a gram per gram, so it's called mass fraction, if we multiplied it by 100%, it would be mass percent. Right? but effectively what it comes down to is the amount of solute per amount of solvent. And those units can change, and you need to be paying attention to what those units are. So let's talk about different types of solutions. The first is going to be an unsaturated solution, which is the majority of solutions that we deal with in chemistry. So it's going to contain less than the maximum amount of solute. So we do not get into it in this class. It is not that the water ran out of space, it's just that there is a maximum amount of types of solvents that can be dissolved into water. So for example, sodium chloride has a maximum solubility of around 6 molar. We'll define what that means later, but it's a moderate amount of sodium chloride. If we had something like nitric acid, its maximum solubility is closer to 16 molar. So it will depend on the type of compound dissolved. Both of those are dissolved in water. So both of those, these are going to be their maximum concentrations. Working concentrations less than this will contain the maximum amount of solute. So those are unsaturated solutions, basically a typical solution you would use. When we hit the maximum amount of a solute that can be dissolved, we call it a saturated solution. So it has now contained a maximum amount of solute that can dissolve. If you have undissolved solute, what it's going to do is just sink to the bottom of the container. It will still go into solution, so we can see it's dissolving, but some of it's coming out of solution, and that's what is causing it to look like to you to not go into solution. Yes, on the microscopic scale, atoms are coming and going, but overall, it looks like nothing is changing on the macroscopic. Macro being big, right? So seeing through your eyes. And this is the idea of recrystallization. So some of that stuff is falling out of solution, comes back, and recrystallizes. So we have our solute, our minute component, and our solvent. It's in some sort of equilibrium, so a forward and reverse reaction with the saturated solution. Some of it is going to be dissolving, matching the same rate that some of it recrystallizes. So again, overall, it looks like nothing is changing over time. So solubility. Things that affect how well a solute goes into a solvent. The first we're going to talk about is temperature. So for most things, right, well actually for all solubility, it's going to depend on temperature. Most solids increase as temperature increases. Gases decrease as temperature increases. So let's take a look. So let me wipe this clean. So we have a solid. Sodium iodide is a solid. We see as temperature goes up, solubility goes up. Same thing with sodium nitrate. Glucose is just sugar. You can find that on your shelf. We see sodium chloride is, even though we think it is super soluble, it's actually moderately soluble to make a salt solution. Things like glucose, which is sugar, is much more soluble. What is not shown here would be if we had solubility of a gas versus temperature. And what you actually see there is the reverse. So this actually explains why something like carbon dioxide, which is a greenhouse gas, is so worrisome when the temperature is increasing in the ocean. So if the temperature of the ocean is increasing, so we're going in this direction on the graph, we see that that solubility in water is decreasing, which then kicks it into the atmosphere, which then compounds the effect of global warming. That's where you get this runaway greenhouse effect. So, two things you can remember this, the way that I teach my Gen Chem students to remember, is that when we're dealing with solids, right, I want you to think of rock candy. So maybe when you were younger, you made rock candy. You would boil water, so be very high in temperature, dissolve a lot of sugar into it, and then wait for it to cool down. And then over the course of days, the sugar would start to crystallize out, and you get rock candy. Why? Because you made a saturated solution, and then as it cools, some of that starts to fall out of solution as candy crystals. On the other hand, think about a gas dissolving in a liquid. I want you to think of either seltzer water or soda, right? On a hot day, if you open a can of Coke or Pepsi or whatever, it fizzes a lot, right? It fizzes a lot. Why? Because when it gets hot, so as our temperature goes up, the solubility of a gas goes down. So when it goes down, then it just turns into a gas, and that's why it gets so fizzy on hot days. Oh, sorry, I jumped the gun on that. I didn't realize. Sorry, that's my bad. I was only talking about, well, on the last slide, let me reiterate. Wait for that to switch over. Right, this is talking about solids. I jumped the gun. My apologies. These are all solids. And it's saying that as solids increase in temperature, their solubility increases. When we're talking about gases, and this is exactly what I just said in that last slide. Oops. We're going to stop at this. What I said in the last slide is that the solubility of a gas is directly related to the pressure. Sorry, guys. Like I said, it's going to take a little bit of time to get used to all this, right? So we're still talking. I'm switching over to talking about solubility of gases again, right? But in terms of pressure, right? Again, we're going to be talking about. I'm going to use soda as an example. So the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. So at higher pressures, more gas is dissolved in the liquid. Why? Right? And why am I using that soda example again? So when you have a sealed can of Coke, right, it's under pressure. When it's under pressure, right, all that CO2, which is that carbon dioxide, is dissolved inside the Coke. Or mostly Coke is water, so it's aquated, right? When you open that pressurized can, right, the pressure is going to decrease. And when that pressure decreases, so P goes down, solubility of a gas also goes down. There's nothing holding it into solution, and it leaves. So think about opening a can of soda. Opening a can, right? And so that's going to end our lecture. I've already gone about 10 minutes over. I promise in the future I'm going to try to keep this to 20 minutes like I promised. It's going to take practice, so bear with me. But I believe this is probably a good way to start off this unprecedented transfer to online classes. So I will see you all hopefully tomorrow.